Hello everyone, I am Savitri Bennur from BSc 3rd semester. Today I am going to explain about my assignment topic, that is numerical problems on a first law of thermodynamics, Joule's Thomson effect, and adiabatic expansion of an ideal gas for reversible and irreversible process. And the first topic is numerical problems on a first law of thermodynamics. Problem number 1. Find the change in the internal energy, thermal energy and work done if 2 moles of a hydrogen at a 3 atm pressure expand isothermally at a 50 degrees Celsius and reversibly to a pressure of a 1 atm. Solution. First we write the givens. R is the ideal gas constant, that is equal to 8.314 joules per Kelvin per mole. N is the number of moles of hydrogen, that is equal to 2 moles. P1 and P2 are the pressures, 3 atm and 1 atm respectively. T is the temperature, that is equal to 50 degrees Celsius. To convert Celsius into Kelvin, add the 273, that is 50 plus 273 equal to 323 Kelvin. From the first law of thermodynamics, delta E is equal to Q minus W. For the ideal gas, delta E becomes 0. So, Q minus W equal to 0 or Q is equal to W. For a reversible process, W is equal to minus nRT ln P1 divided by P2 or W is equal to minus 2.303 nRT log P1 divided by P2. Put the all values in this equation, then W is equal to minus 2.303 into 2 into 8.314 into 323 into log 3 by 1, where log 3 is equal to 0.477. By multiplying all these, we get minus 1410 calories. To convert calories into joules, multiply 4.18. Minus 1410 into 4.18. Multiplying these two, we get minus 5893 joules. We know that W is equal to Q and Q is equal to minus 5893 joules. Note, Q is a negative, so heat is evolved during the reaction. Problem number 2. A gas contained in a cylinder pitted with a frictionless piston expand against a constant external pressure of a 1 atm from a volume of a 5 liter to volume of a 10 liter. In doing so, it absorbs 400 joules thermal energy from its surroundings. Determine change in the internal energy for the process. Here we are going to determine the change in the internal energy for this process. Solution. Firstly we write the givens. P is the pressure, that is equal to 1 atm. V1 and V2 are the volumes of a cylinder, that is equal to 5 liters and 10 liters respectively. Q is the thermal energy, that is equal to 400 joules. Now we are going to determine the delta E, that is change in the internal energy. From the first law of thermodynamics, delta E is equal to Q minus W. This is the equation number 1. We know that dW is equal to minus PdV. Integrating on both sides, we get W is equal to minus P V2 minus V1. Putting the all values in this equation, that is minus 1 bracket 10 minus 5, then it becomes minus 5 liter atm. To convert liter atm into joules, multiply 101.3 joules. Minus 5 into 101.3 is equal to minus 506.5 joules. Substituting the W and Q values in equation number 1, then the equation number 1 becomes 400 joules minus bracket minus 506.5 joules, that is minus of minus is equal to plus, so 400 plus 506.5 joules, it is equal to 906 joules. Change in the internal energy for this problem is equal to 906 joules. And my second topic is numerical problems on a Joule-Thomson effect. Problem number 1. A 573 Kelvin and pressure 0 to 6 megapascal, the Joule-Thomson coefficient of a N2 gas can be represented as mu Jt is equal to 0.14 minus 2.533 into 10 raised to minus 2 megapascal. Assuming this equation to be independent near 573 Kelvin, find the temperature drop which may be expected in the Joule-Thomson expansion of the gas from the 6 megapascal to 2 megapascal pressure. Firstly, we write the givens for this problem. T is a temperature that is equal to 573 Kelvin. P1 and P2 are the pressure that is equal to 6 megapascal and 2 megapascal. Mu Jt is a Thomson coefficient that is equal to 0.14 minus 2.533 into 10 raised to minus 2 pressure per megapascal. Thomson coefficient equation is mu Jt is equal to dou T divided by dou P in a constant enthalpy. This is the equation number 1. To find the temperature drop, the equation number 1 becomes dou T is equal to mu Jt into dou P. Put the values of mu Jt, then dou T is equal to 0.14 minus 2.533 into 10 raised to minus 2 into dP. Dou T is equal to 0.14 dP minus 2.533 into 10 raised to minus 2 pressure per megapascal into dP. Integrate the above equation. Here 0.14 and 2.533 into 10 raised to minus 2, these are a constant. So delta T becomes 0.14 integrate dP with a limit P1 to P2 minus 2.533 into 10 raised to minus 2 integrate P divided by MPa dP with a limit P1 to P2. Integration of a dP is P and integration of a P with respect to dP is P square divided by 2. Put the limits in the equation. Then 0.14 P2 minus P1 minus 2.533 into 10 raised to minus 2 bracket P square divided by 2 with a limit P1 to P2 into 1 by megapascal. 0.14 P2 minus P1 minus 2.533 into 10 raised to minus 2 P2 square divided by 2 megapascal minus P1 square divided by 2 megapascal, where P2 is equal to 2 and P1 is equal to 6. So 0.14 bracket 2 minus 6 bracket complete minus 2.533 into 10 raised to minus 2 bracket 2 square divided by 2 minus 6 square divided by 2 bracket complete. 0.14 bracket minus 4 bracket complete minus 2.533 into 10 raised to minus 2 bracket 4 divided by 2 minus 36 divided by 2 bracket complete is equal to multiplication of a 0.14 and minus 4 is equal to minus 0.56. So minus 0.56 minus 2.533 into 10 raised to minus 2 bracket 2 minus 18 bracket complete is equal to minus 0.56 minus 2.533 into 10 raised to minus 2 into minus 16. Multiplication of 2.533 into minus 16 is equal to 40.528. So minus 0.56 plus 40.528 into 10 raised to minus 2 minus 0.56 plus 0.405 is equal to minus 0.514 Kelvin. Temperature drop is equal to minus 0.155 Kelvin. Problem number 2. The van der Waals constant A and B for a hydrogen are 0.246 dm raised to 6 atm per mole square and 2.67 into 10 raised to minus 2 dm cube per mole respectively. Calculate the inversion temperature of a hydrogen. Solution. Here A and B are a van der Waals constant for a enthalpy, where A is equal to 0.246 dm raised to 6 atm per mole square. B is equal to 2.67 into 10 raised to minus 2 dm cube per mole. R is equal to 8.31 joules per mole into Kelvin, or R is equal to 0.0821 dm cube per Kelvin and per mole. Here we are going to find the inversion temperature. We know that temperature inversion is equal to 2A divided by RB is equal to Ti is equal to 2A divided by RB. Put the all values in this equation and simplify it. Then we get 2.247 into 10 raised to 2 Kelvin is equal to 224.7 Kelvin. To convert Kelvin into Celsius, subtract minus 273.15 in 224.7. Then we get minus 48.45 Celsius. Then inversion temperature is equal to minus 48.54 degrees Celsius. And my third topic is work done in an isothermal and adiabatic expansion of an ideal gas for a reversible and irreversible process. Problem number 1. Calculate the work done when 3 moles of a nitrogen gas at a NTP expand adiabatically so that its temperature falls from 273 Kelvin to 263 Kelvin. Here R is equal to 8.31 joules per Kelvin per mole and gamma is equal to 1.4. Firstly, we write the givens. N is the number of moles that is equal to 3 moles. T1 and T2 are 273 Kelvin and 263 Kelvin respectively. We know that work done expression for a adiabatic process that is equal to W is equal to NR divided by gamma minus 1 into T1 minus T2. Put the all values in this equation and simplify this. Then we get 623.25 joules. Work done is equal to 623.25 joules. Problem number 2. Calculate the work done for the adiabatic reversible expansion of 2 moles of an ideal gas at a 273.2 Kelvin and 20 atm to final pressure of a 2 atm. Solution. Firstly, we write the givens. Heat capacity at a constant pressure is equal to 5R divided by 2 per moles per degree, and heat capacity at a constant value that is equal to 3R divided by 2 per mole per degree, where R is equal to 8.314 joules per mole per degree and T1 is equal to 273.2 Kelvin and P1 is equal to 20 atm and P2 is equal to 2 atm. Step 1. To calculate the value of a T2, the final temperature using the equation, that is T2 divided by T1 power gamma is equal to P2 divided by P1 power gamma minus 1 is the equation number 1, where gamma is equal to Cp divided by Cv. So gamma is equal to 5R divided by 2 into 2 divided by 3R. Then gamma becomes 5 divided by 3. Substituting the value of a gamma in equation number 1, that is T2 divided by 273.3 raised to 5 divided by 3 is equal to 2 divided by 20 in the power pi divided by 3 minus 1. T2 divided by 273.3 raised to 5 divided by 3 is equal to 1 by 10 raised to 2 divided by 3. T2 divided by 273.3 is equal to 1 divided by 10 power 2 divided by 3 into 3 divided by 5. T2 is equal to 273.3 is equal to 1 divided by 10 power 2 divided by 5. T2 divided by 273.3 is equal to 0.39810. Then T2 is equal to 0.39810 into 273.3. T2 is equal to 108.8 Kelvin. Step 2. To calculate the maximum work under a adiabatic condition, the equation becomes maximum work done is equal to nr T2 minus T1 divided by 1 minus gamma, where r is equal to 8.314. Put the all values in this equation and simplify, then we get 4100 joules or 4.1 kilojoules. Work done under the adiabatic process is 4.1 kilojoules.